Okay. Oh, I forgot to share my desktop. Okay. So, normal stuff. All right, so I'm going to, I guess I can do number, I'm not going to do all of these. Everybody should have gotten number part B answer there. 50%. Cute little picture of a normal. Once in a while, somebody forgot to draw their normal distribution. So normal probabilities. Do the T's. Which question is this? Number 5, is that right? Yeah, so number 5 was about the standard normal. What is the mean of a standard normal distribution? The standard normal, it's 0. And the standard deviation?
1.
Is 1. And the standard normal is a distribution of z-scores. So this would be the z-axis. 0 is already always in the middle. This would be about 1, 2, and 3 standard deviations. -1, -2, -3 over there. And we were asked less than 2. So probability that z is less than 2. So first thing I want to do is identify where 2 is roughly, and then shade what I'm trying to find. So that would be less than 2, and it goes to the left forever. Since it's a less than, that's exactly what the normal distribution formula on Excel does. So to find a normal probability on Excel, we use the norm.dist. Oops. And the norm.dist wants to know a few different things. It wants to know what's your x or z value, 2. What's your mean, 0. What's your standard deviation, 1. And is this cumulative or not? Do we ever do not cumulative with a normal distribution?
No.
Never, ever, ever.
If it's less than 2 instead of less than or equal to 2?
An individual number is insignificant.
Okay.
So the probability that z is less than 2 is exactly the same as the probability that z is less than or equal to 2.
Okay.
An individual number doesn't matter. So those two are the same. That formula right there gives that answer. And I calculated that to be approximately 97.72%. So that's this area I found right here. Two is basically that point on the z-axis or the x-axis. All right, let's skip down to part C, because these next two calculations are very relevant to what we're moving on to today, which is chapter 8. So part C, which one color, asks, what is the probability that a z-score is between -2.327 and +2.327? Drawing a picture of that. In the middle of a z-score is always 0. 3 is out on the edge of the tail. And so then I want to identify here about where -2.3727 is, and that's right about here is my best guess.
Is that 1?
Oh shit, right. Is there an undo button on this? Oh yeah, look at that. 1, 2, thank you. That'd be about right here. And then -2.327. So it's about 2 1/3-ish. And so I want to find the area in between here. So the normal dist, so if I use the upper number for a minute, what it's going to find is norm.dist. If I give it 2.327, mean of 0, standard deviation of 1, always cumulative, it's going to find the whole left tail there, which is more than what I want. So then I have to cut out, take away the lower tail. I want to subtract from that the norm dot dist of the lower part, negative 2.327011. And when I did that, I got pretty damn close to 98%. So I just entered this in one cell on Excel, and I got about 98.003%. Calling it 98% was more than sufficient. So we're going to use this idea in a little bit with what are called finding confidence intervals. So for example, maybe this picture represents thermometers that are designed to very accurately measure freezing temperature, right? 0 degrees Celsius. Okay. Are all thermometers going to be perfect? No, they're all going to be a little bit different. So some of them might call 0 exactly right here. Some of them might call 0 right there. Some of them might call that 0. Some of them might call this 0. So what I'm hoping is that 98% of the thermometers I make as a manufacturer fall in this region right here because I think that's close enough to 0. Okay. And so we would want to design experiments to see if we can get our thermometers to work in that region. So when I do something like that, this region right here, so here I would just abbreviate that CL. I want my CL to be 98% or 0.98. What's left to go in the tails here? 2%. They have 2% to split. So how much does this tail right here get?
1.
So this tail right here would be a 1% tail. What's in this tail on the left here, where the X is? Yeah, that's also 1%. So if there's 1% probability below negative 2.327, we would call negative 2.327 the first percentile. What's a percentile mean?
Quartile.
Not quartile. Well, quartile is like 25 or 75.
That much, that percentage of people have like that score or
below, yeah. So if a thermometer said this was 0 right there, I believe that the thermometers I make, only 1% of the thermometers I make call that or below 0. Right? So it's the marker, right? Yeah. So what this picture also calculates here is P1, the first percentile. And according to this, the first percentile for z-scores is the number negative 2.327.
So in turn, would that be, would the 2.327, would that be like 99%? Since
Yeah.
you said there was only 1%.
So yeah, so since I have 98 in the red area and 1% below, that means the positive 2.327 would be the 99th percentile. And we'll double check that in a minute. So according to my picture, P99 should be equal to about 2.327. So that number is right there, what we call the 99th percentile.
Now say that definition again.
Okay, so for 99, 99% of z-scores, or thermometer readings, I'm going to call them z-scores for now, are at or below a score of 2.327. So another application of this, to get into graduate school, I had to take what's called the GRE, the graduate record exam. And on the graduate record exam, you're given a percentile, you're given a z-score, and a bunch of other information about how you did compared to other people that took the test. And so suppose somebody got a 2.327 z-score, on the graduate record exam. That means their score was the same or better than 99% of the other people who took that test. Okay, it's a ranking, a position. Okay, so that's percentile. Anybody remember what formula Excel uses to do percentiles with normals? The inverse, yeah. So to do normal percentiles, we use the formula called the norm inverse. This pen is totally freaking out. So norm dot inverse, I think there's just a norm inverse without a dot. And that takes a couple things. It takes the probability that you're looking for, it takes the mean, and it takes the standard deviation.
I'm going on the game, so I understand.
What probability am I talking about here?
The 99%.
Okay, or 1%, is it a left or a right tail? Yeah, always a left tail, and that's something we got to remember when we use it, because if somebody asks us, like, what's the top 10%, I can't find that directly. I have to do a little subtraction to find that. So the probability here is always the left tail probability. So for the 99th percentile, I would give it the norm dot inverse of 0.99, comma 0, comma 1, because I'm talking about z-scores. And my computer to 3 decimal places told me that was 2.326, which is close to the number I have above. So I could just double check that. Keyboard P99, I'm not typing, oh, there goes, slow, equals norm dot inverse. Oops, I didn't spell right. Norm, there we go, dot inverse, 0.99, comma 0, comma 1, close enter, 2.326, let's blow that up. Come on. How's that? There we go. So about 2.326-ish. What am I going to get if I try to find P1, the first percentile? So let's look back at the graph. Go right here. So given the symmetry here, if 99% puts 1% above, the first percentile puts 1% below, so I guess you get the mirror image of that z-score. Negative 2.327. Yeah. So let's just double check to see if that matches the symmetry of my graph, and it better, otherwise the world's going to end. Norm dot inverse of 0.01, right, 1%, mean of 0, standard deviation of 1, and there's the negative of that number. And it's just rounding differently, but it's the same number. Okay. All right, let's do one more, then I need to move on. 6 or 7. Let's do 7. A note on number 6. So this was number 5 right here we were doing. Number 6, there's a problem very much like it on page 350 in the book. All right, so this problem is about percents of fats, calories. And we are told that a person in America consumes each day, normally distributed, so on average people have about 36% of their calories from fat. We're just going to call it 36. and the standard deviation of the population is believed to be 10. And the first problem we're asked is for an individual, what's the probability that the percent of fat calories consumed is more than 5? So if my random variable is x, percent of fat calories consumed, then for part A, I want to know what's the probability that x is more than 5, which would be greater than 5. Does it matter if I put an equal to here? Because it's normal, yeah. With a binomial, it totally matters. Huge difference. With normal, it doesn't matter. All right. So that's going to be the norm dot dist of 5, 36, 10, 1. There's one problem with my calculation here. What am I really calculating there? What does the norm dist calculate? Left tails or right tails? It does left. I want the right, so I have to adjust this with a 1 minus to get it right. Now, before I even do that, what should I be doing right now? I should draw a picture to just double check what I'm looking for. It'll give me a rough idea of what the answer is going to look like. So here's my picture. In the middle is exactly 36. And then 1, 2, and 3 standard deviations jump by 10. So that'd be 36, 46, 56, 66, and so on. Going the other way, I'm counting backwards by 10. So let's see, 36, 26, 16. This would be 6 right there. I want 5, which is just a hair to the left there. So any guesses as to what this might be? It's going to be pretty damn high, like 99%. That's most of the graph right there. So we can guess by looking at this, it's going to be 99%-ish. So whipping out that calculation. So we have a mean of 36, an STD of 10. We want to know what is the probability that x is greater than 5, which is equals, I got equals 1 minus the norm dist of 5, comma, 36, comma, 10, comma, what's always next?
1.
Always a 1 for the normal. Oops, that's not a 1. There we go. Enter, and I get 99.90-ish, 99.9%, which is roughly what I was expecting from the picture. All right, so sentence might look like this. About, that should be capital A, 99.9% of Americans consume more than 5 what? So look back at what X is, percent of fat calories, or percent of calories from fat, I think is the way it's mentioned. Percent of fat calories. More than 5% of fat calories. So if I were to like call 5 a percentile, what percentile would it be? It'd be smaller than the first percentile, because it's actually less than 1%. Okay, what would 36 represent in terms of a percentile? The 50th percentile, right? And so in the next question, we're asked to find where the 25th percentile lies. Okay, so it's some number between 5 and 36. We just don't know which one. So that's the next question. What is the 25th percentile? Did I get that right? Yeah, first quartile is the 25th percentile. So we want Q1, which is the 25th percentile. So question really could be stated as what number of fat calories has 25% of Americans below it. Oops. Or more specifically, it would be at or below. Okay, so we're going to figure that out now. Drawing a rough sketch of it. Every time we do a normal calculation, I'm going to redraw a picture. So there's 36. That right there is about 26. Right there is about 16. Right here is about 6. So we're trying to find a number somewhere in here so that 25% of the probability is to the left there. I have no idea where it is right now, but I know I'm looking for a left tail somewhere. What formula do I use for P25? Norm inverse, yeah. So norm dot inverse of 0.25, 25%. Mean here is what? 36, STD? 10. Norm inverse doesn't take another argument because it's always cumulative. There's no other option. And so I asked Excel that, and Excel told me it was about 29.26. Oops. So there's 26, there's 36. What's in the middle? Like 31, so 29 is maybe about there. So right about here has 25%. Oops. 25% of the data below this number. It's supposed to be 5, believe it or not. Does that seem reasonable? Well, let's think about that for a minute. This is 1 standard deviation below at 26, right? What percent of the data is supposed to be within 1 standard deviation on each side? No, not 50.
60.
Within 68%. Okay, right? What's half of 68? 34, okay. So that means 34% would live between 26 and 36. So 34% of Americans eat between 26 and 36 fat calories a day. Okay. Also, I can go the other way. From 36 to 46, 34% of Americans eat between 36 and 46 fat calories a day. That's what that tells me. Now let's just, okay, so this region from here to here is 36%, right? What's in the whole left tail from the middle? 50. What's 50 minus 34? 16, yeah. So if I measured the area from this line to the left forever, that would be about 16. So does it make sense the 25th percentile has to be somewhere to the right of that? 1 standard deviation below? Because this percent from there to there is about 16%. So I'm just trying to get an idea. Did I totally screw this up? Do I have some other numbers that make it seem about right? All right, one more, and then we need to move on. Let's do C. C, here I'm given 16 individuals are chosen at random, and we're only looking at their average. So average fat, whoa, wrong letters, right letters, wrong order. Average fat calories consumed. Consumed, there we go, by 16 Americans. Average is what we call X bar, not X. Now, once I start talking about the average of the group, I got to be a little careful. What theorem applies here? What idea that we went over? This is the central limit theorem, and the central limit theorem says that the mean of a sample, or a bunch of samples, in this case 1 sample, is going to be approximately the same as the mean of the population, which for us is what here? I think 36. Mm-hmm. However, the, let's call it S, the sample standard deviation is going to be approximately the population standard deviation, but tweaked. How do we tweak it? Divided by the square root of the sample size, n. So for us, that means we want to take our 36 and divide by the square root of 16. If we clean that up a little bit, oh shit, not
Wait, no,
36.
10.
10, thank you, yeah. Didn't look right. 10. This is population standard deviation divided by square root of 16. So let's see, square root of 16 is 4. You cut 10 in half, you get 5. If you cut 5 in half, you get 2.5. So this is equal to 2.5. So in order to do a calculation based on the average of 16 people, I have to use this as my mean and this as my standard deviation. So the next question says, well, what's the probability that the average of 16 people is greater than 5? So that calculation, since the right tail is a 1 minus, it's still normal. My x value is still 5, but it's not x, it's x bar, it's an average. 36 stays the same. Standard deviation has to shrink because I'm talking about the average. I lost information, so I have to shrink the standard deviation, and then a 1. Just do a quick sketch of that. If 36 is in the middle, then just to the left of that, 1, 2, and 3, minus 2.5 is going to give me, what, 33.5? Minus 2.5 again gives me 31. Minus 2.5 again, 28.5? Is that right? Whoa, where the hell does 5 live? Way off my page. So I'm just going to go dot, dot, dot. 5 is somewhere way out there. And I want to find the area above 5, which is all of this. Can anybody want to wager a guess as to what that area is going to be about? It's going to be pretty damn close to 100%. I don't know if Excel will be able to tell the difference. So let's just double check. Whipping out Excel. So I have a new mean of 36 and a new standard deviation of 2.5. And repeating the probability above. Excel says it's 1. Maybe I could ask for more decimal places. Let's see which one is increased decimal. Excel can't, oh. Excel says, yeah, the best I can tell, it's 1. I'd stop there. So that's that one there. So what's the chance a group of 16 Americans consumes more than 5 fat calories per day? It's a sure thing, group of 16. Yeah. What about an individual? Still pretty high chance. So there's some review. I hope that helps. Let's stop this thing.